Hi, little one. Alrighty. Cool. Let's go ahead and get started. We have just kind of one last little bit here. We're going to be talking about factors that affect acid strength, and then we'll do some more practice with looking at some of the salts to determine what the pH would be of a given solution of that salt. So, just one thing to point out. Remember that acidity of a solution. Wow. Wait, I can fix that. Yeah, there we go. Is concentration dependent. So how acidic the pH of your solution, that really means, is concentration dependent. So it depends on how concentrated your acid is. However, the acidity of a compound has nothing to do with concentration. So it doesn't matter how your concentration of HCl, it's still going to be a strong acid. But the pH of that solution will therefore depend on its concentration, but the acidity of a compound, aka its pKa, has nothing to do with its concentration. pKa is going to be a constant at a given temperature, so we're going to see that we're going to kind of learn some factors here to kind of just predict, without having to look at pKa values, the acidity of particular acids. So, really, the biggest part here is the strength of an acid is dependent on my spelling of the word strength. What it really comes down to is a couple of factors, but the most important one deals with the stability of the conjugate base. That's really what is going to be the most important factor in determining how strong an acid is going to be. There's going to be a number of ways we can stabilize conjugate bases, but typically we're going to look at a couple of those. We're going to see that it all deals with how well does A minus deal with its negative charge. So ones that can really handle that negative charge well will be very stable, and as a result, you're going to have a stronger acid. So remember, again, we have our generic equilibrium here. So remember that chemistry is all about how reactive things are. If this is stable, that means it's unreactive. That means it's not going in reverse. This is all kind of a relative scale. And so therefore, Ka will go up because your A minus concentration and H plus concentration will be kind of maintained for longer. And remember, that means pKa goes down. So pKa down one means a stronger acid. All right, so there's a couple of factors here we can look at. One of which is going to be resonance. That's going to be one factor here. So we're going to see there's a category of organic acids called carboxylic acids. And we're going to take a look at what those look like. I guess I should explain how these molecules look. This is acetic acid. If I were to draw the Lewis structure, that's what this molecule looks like. But in organic chemistry, we often just don't draw carbons in. We just draw these lines instead. And this is ethanol over here. We're going to see that the pKa of this one, somewhere around the order of 5. But for ethanol, it's about 15. The reason for that is if we look at the conjugate bases of these, so let's just go ahead and get rid of the H. We'll make them into A- instead. So those have a formal negative charge on them. In ethanol, or the ethoxide ion, there is nowhere for that negative charge to go. But with the acetic acid, or a general carboxylic acid, we're going to see that we can actually resonate and form. Here, let me erase this one. We don't need to see that. If we resonate this one, we can push our negative now onto the other oxygen. Thereby, we delocalize the negative charge. So that extra bit of electron density in there, we're able to move it around. And delocalizing a charge will increase its stability. So charges are not stable, but we're kind of now sharing the burden between a couple of oxygens instead of just one. So we can shift that negative charge between those oxygens. It'll just go back and forth in between them, and that's going to delocalize it. So remember, resonance, as we studied last semester, delocalizes your electrons. So you can move them around in between the oxygens. This poor ethoxide cannot do that. There's nowhere to resonate. And so as a result, it's going to be much less acidic, the ethanol is. And if we compare that, that is a 10 to the 10 difference. So acetic acid then ethanol. Simply because of resonance. So you can see here that's a very kind of important consideration. So just stabilizing your conjugate base a little bit, you can make your compound, what is that going to be, 10 million times more acidic? No, 10 billion. 10 billion times more acidic. Just think about that. I left my tea in the microwave. Hold on. I'll be right back. 10 billion times more acidic, just for throwing in resonance in there. So, as you can see, just stabilizing that a little bit makes it much stronger of an acid. So resonance is one way that we can kind of accommodate charges like that. Another way is the identity of the atom where the acidic H is, the acidic proton is. So, for example, if we have some organic molecules here, and let's go ahead and look at some of these. Again, the pKa of this one is going to be about 15. Let's look up the pKs of the others. Ethylamine pKa. That's its pKb. What's its pKa? I don't want the conjugate acid. Blah. It should be in the 30s, if I remember correctly. Yeah. So we'll say this is about 35. So losing a proton off this ammonia, or amine group. For the thiol, let's see. Let's take a look. Those are going to have pKa's roughly in the 10-ish range. So we're going to see here that we can look at the identity of the atom on which your acidic H is located to get some information about how acidic those atoms happen to be. And so if we go ahead and draw our conjugate bases here, no resonance in any of these, but we're going to see that the only difference is that one atom, right? The different elements there. We're going to see that sulfur is much larger than oxygen and nitrogen, right? It's got an extra shell. It's in a period below it. And as a result, if you want to think about kind of charge in terms of concentration, here's a sulfur atom and an oxygen atom. If these both have a negative charge, we can see that this charge is more kind of concentrated here. If we take a look at that. So if we want to pretend concentration, remember, is like solute over solvent. So there's a volume component there. So because oxygen has a smaller volume than sulfur does, its charge is more concentrated and less stable. On the other side, sulfur is bigger and can therefore kind of accommodate that negative charge a little bit more. Just because it's bigger, it's got more room for those electrons to zip around, and it can accommodate the extra electron a little bit more nicely, and its kind of charge is going to be less concentrated, and so it's going to be a little bit more stable as a result. And so that means more stable. All right, and so as a result, because it's more stable, it's going to be a stronger acid. The HA form is going to be the stronger acid, comparably. So again, because A- is a bit more stable, we're going to see that HA is going to be a stronger acid for the sulfur one. And again, we see that the sulfur is going to be, 10,000, 100,000 times more acidic than the oxygen-containing compound there, just because the sulfur is larger. We call this the polarizability. And that's the ability to kind of accommodate the charge. It kind of depends on multiple things here. So it depends on size and electronegativity. But suffice it to say, if we look at the periodic table, we can kind of come up with our general trend for polarizability. Generally, we're going to see that polarizability increases as we go down and increases as we go to the right. We're going to kind of exclude the noble gases because they're not going to make compounds with hydrogen. But we're going to see something like iodine down here is going to be really polarizable because it's very large and still relatively electronegative compared to something like fluorine, which is why HF is a weak acid, and the Kas of these continue to go up. So the Kas will increase in this direction. So HI is actually going to be our strongest binary acid. So if you were to just compare these, HF is not even a strong acid. The other three are. But if we're to kind of just compare them, HI is in fact even stronger than HBr, which is stronger than HCl. So we're going to see this is going to be a trend here. So because iodine is more polarizable, it can accommodate that charge better. The iodide ion is more stable, and as a result, since that's the conjugate base of hydroiodic acid, HI is going to be a stronger acid. Relax, Creech. You're okay, buddy. All right, does this kind of make sense? So we're only going to worry about these kind of two factors here with these particular patterns. If you end up taking OChem, you're going to learn a lot more about inductive effects and hyperconjugation and other fun terms. But for us, that's what we're looking at. So just kind of in summary of this section, if it can resonate, that means it's more stable, which means it's a stronger acid. And the second thing we looked at, if A is more polarizable, it's more stable. I guess I should say A minus or A whatever. And that means it's a stronger acid. All right. So we're going to see here that as a result, that category that we talked about, carboxylic acids, which have this kind of idea, whatever they happen to have on the other side, these are the carboxylic acids. So that would be something like acetic acid, oxalic acid, propanoic acid. All of these are carboxylic acids. Benzoic acid. They're going to be more stable than just alcohols, which are just those plain OH groups, because they can resonate. So they have two oxygens there, they can resonate in between. All right, and then we saw that, for example, HI, this is why HF is a weak acid, but something like HCl, HBr, HI are strong acids. Because fluoride is so small, it's not going to be able to accommodate the charge as well as the other three potential halides, and so that's why HF is a weak acid. All right, the kind of last component here that we didn't necessarily talk about, it's not really related to the stability of the conjugate base, but it also is important with the acid in general. The bond length between H and A is important. So a longer bond is weaker, and that means we're going to have a stronger acid. It's easier to remove that hydrogen if you have a very large A. And so that's another reason that if we look at the HCl bond, the HBr bond, and the HI bond, iodine is the biggest one, right? If we go ahead and look at these, let's see, how about, let's see, HI bond length. Let's see, the HI bond, oh, thank goodness. we have some bond lengths here. Here, let's even look at HF. HF's bond length is 92 picometers. For HI, it's 161. How about HCl? Let's look at some numbers here just to put those out there. HCl is 129. And then HBr, let's get that. HBr, single bond. What are these? These are bond energies. I want bond length. 141. Okay. Picometers. Cool. So, as we can see here, these bond lengths are getting longer and longer. We see that this one is the most acidic, and up here we have the least acidic. So again, the easier it is to pluck off that proton, is going to come from a longer bond. Longer bonds are always weaker. Weaker bond means easily broken. Easily broken means more reactive. And so the more reactive your acid is, the more acidic it is. The more likely you're going to dissociate that H+. It's going to be easier. So, I mean, you can see the HI is going to be twice as long, pretty much, as HF. So that's going to be kind of the third factor we're looking at with all this stuff. So, and this kind of contributes to the polarizability a bit as well. It's kind of a similar idea. The larger your atom is, the more polarizable it is. But it's also going to mean you have a longer HA bond length, and therefore a weaker HA bond. Alrighty. Any questions on those ones? Of course, you can always look at a chart of pKa's to, easily find these things, but, sometimes you may not have a particular pKa available to you, and so you may need to be able to just kind of guesstimate what's going to be more acidic. All right, so you're going to look at these factors. Alrighty. Again, this is probably something we're going to definitely cover more in OChem, but it's important that while we're discussing acids and bases, what factors contribute to the strength of an acid. And, for bases, it's all the same stuff, except you replace the word acid with base, and you replace conjugate base with conjugate acid. So for that, everything's the opposite. So the more stable your conjugate acid is, the more strong your base is. So it's all the same stuff, just in reverse. All right? So in that case, like Creech, if we want to go ahead and look at a couple of salts, I'd be happy to entertain that. We can work on some pH problems here. All right, so that's kind of the end of chapter. What chapter are we on? 16. I did promise you we would do a couple of Lewis acid, Lewis base things, didn't I? So let's do another couple of examples here. All right. This is an important reaction for organic chemists in something called a Friedel-Crafts alkylation or acylation. It's an important catalyst there. And the reason for that is because of this reaction that takes place. So this is an acid-base reaction, despite the fact there are no hydrogens in this particular scenario. But this is going to be one that deals with Lewis acids and Lewis bases. So if we go ahead and kind of draw these, if we look at these, hopefully right away, we can see what the acid and what the base are going to be. Remember that bases are going to be donating lone pairs, and acids are going to be receiving lone pairs. And so at the end of your reaction, your acid will have an additional two pairs of additional two electrons, and your base will have lost some electrons. So if we were to draw this, Okay, here we go. We can see that, I mean, actually, we don't even really have a choice. This one has to be the base, right? It is full of electrons. It cannot take any more lone pairs. And in fact, aluminum doesn't have any lone pairs to give. So that's another easy way to tell. We're going to see that this chlorine will go ahead and latch on. And we're going to see that this chlorine now has 3 lone pairs, whereas before it had 4 lone pairs. This aluminum had 3 bonds, now it has 4 bonds. The aluminum now has a negative charge on it. And so, hold on, I'm about to sneeze. We're going to see that that is going to have more electrons now as a result, so the aluminum is going to be receiving a lone pair from that chloride. All right, and so that's going to be kind of what we're looking at with all of these. So despite the fact that there is no hydrogen here, we can still have acid-base reactions happening. The Lewis acid and base definition is a bit more broad, does not even include protons. It just deals with lone pairs. Again, however, most of the stuff we will talk about that's going to be called an acid will be mostly Bronsted-Lowry acids, where we see proton donors as our acids. So, however, Lewis acids are going to be important catalysts for a lot of reactions, and so those are important to distinguish. So, generally, we'll refer to things specifically as Lewis acids, but most Bronsted acids, we just say acids. So we don't necessarily worry about saying Bronsted every time. All right. Let's see. What would another one be? How about... Let's see the homework again. Let's see if we've got some good examples here. Let's do one of your homework problems. We already did so many of these. Okay, that one we can do. Yeah. This is going to become nitrite and... I'm sorry, this is OH minus. I mean, right now we can already see what the Bronsted acids and bases are. Right, we can see nitrate is losing a proton, therefore it's an acid. But let's look at it in terms of Lewis stuff. So, nitrous acid here. What are we going to have with this? Oh, I really should not draw it that way. There we go. That is our nitrous acid structure. We have OH minus nitrite, and water. So if we're looking at this in terms of what's happening with lone pairs, we can see here that what's happening in this reaction is we're going to be breaking that bond, forming a lone pair onto our oxygen, and that hydrogen is going to be basically plucked away by the hydroxide. We can see now this oxygen here has 3 lone pairs, this oxygen has 2 lone pairs, whereas this one previously had 3 lone pairs, and this oxygen had 2 lone pairs. And so we can see that very clearly what's happening here is we're going to be increasing our lone pairs for the nitrite, and decreasing for the hydroxide. So we know that this will be our acid. It's both a Lewis acid and a Bronsted acid. And then our hydroxide, of course, is going to be our base, both in terms of Lewis and Bronsted. So if there's a hydrogen involved, you can kind of cheat. But if you look at that previous one, we definitely did not have a hydrogen involved. So sometimes you may have to just use your noggin a bit. Cool. So let's go ahead and look at some salts then. So in Discord, I put up a chart just for ease of access of a bunch of different pKa's and Ka's, so we can take a look at some salts and see. All right. Okay, let's go ahead and take a couple of examples here. Let's look at potassium benzoate. Let's look at what else do we have. Yeah. Dihydrogen arsenate. Let's look at ammonium acetate and ammonium carbonate. And let's see what we can do with these ones. Actually, let's look at another one. Let's look at let's look at that. And then lithium nitrate. Okay, so let's look at all of these and see what the heck's happening with them. So if we want to figure out what's happening with these, potassium benzoate, perhaps something that we are not familiar with its structure or formula, but this is a very common preservative. It's used in a bunch of things. Let's go ahead and look at our chart here. We do see that we have something called benzoic acid. If we look at our, if we remember our names, something that ends in ic acid comes from an 8. So benzoic acid does come from benzoate. So benzoic acid has a pKa of 4.19. Which means that the pKb will equal 9.81 for the benzoate ion. Right? We saw that we can use that relationship between the pKa and pKb of a conjugate pair because they would be equal to 14. So if the pKb of benzoate is 9.81, and remember that potassium, being a large, lowly charged cation, doesn't really have a conjugate, we're just looking at something that is going to be a base, right? So we can get rid of this benzoic acid. We don't have benzoic acid in there. Potassium does not have a pKa, right? There's no hydrogen on it to deal with. It also doesn't really have a pKb because potassium, again, does not can't have an H plus to begin with, so it's not an A minus, so it can't even have it. So if we notice, we have benzoate which has a pKb, so we're going to see that this is going to be basic. So we're going to expect a high pH for a solution of potassium benzoate. So remember, we have the conjugate of a weak acid in here. And so that means it's a weak base. So benzoate is a weak base. Potassium is nothing. So as a result, this is a weakly basic salt. So if we were to make a solution of it, we're expecting it to be basic. All right, if we take a look at that arsenate ion there, We might have to look at that a little bit more closely, but let's take a look at its pKa. If we look at the hydrogen arsenate, dihydrogen arsenate, where is that going to be? Its pKa is about 7.10. Which means its pKb, actually its pKb we're going to have to look up, right? Because the pKb would be the reverse for the first removal of the proton, right? So its conjugate here, the other conjugate, if we look it up, the pKa of this guy is 2.30. Sorry, I have it on the other monitor and it's pretty small. So that means the pKb of that guy, of this base, is going to be 11.70. So the pKb for the dihydrogen arsenate is 11.70. Its pKa is 7.10. So what's going to win here? If we had something of sodium dihydrogen arsenate, let's say, we're expecting that this will be acidic. The pKa is lower than the pKb, so we're going to expect that a solution that has this dihydrogen arsenate ion will be acidic. Hi, little dude. I'll play with you in a bit. I still gotta teach. All right, does that one make sense? Alrighty. So, now we have some complicated ones. These two are both going to fall under our complicated category, meaning we're going to have to do some evaluation here. We can't just say right away, okay, this is an acid or a base. Like the potassium benzoate, you can say right away it's basic. You have an anion in there. That is a weak base. Cation doesn't matter. However, we have a cation which has a pKa of 9.25, according to our chart. And then we have acetic acid, which has a pKa of 4.7, or so. Where is acetic acid? Yeah, 4.75. Which means that the acetate's pKb is 9.25. Isn't that convenient? And so, as a result, what do we think is going to happen here? The pKa and pKb are the same. pKb of our base, yeah, exactly. So overall, this one will be neutral. Because it's going to be acting as an acid and a base exactly the same. And in fact, to 2 sig figs too. So this will be for sure neutral. All right, creatures outside borking. Let's hope the neighbors don't get mad. For this next one, we're going to have, again, ammonium. So we're going to have that pK of 9.25. For carbonate, let's have a look here. It looks like carbonic, or the hydrogen carbonate has a pKa of 10.32. So the pKb for this, for carbonate, will be 3.68. And so as a result, the pKb wins out in this case. So this one will be basic, because this pKb is going to be lower than our 9.25 for our ammonium. And remember, the P scales are powers of 10, right? So it's a million times more basic than ammonium is acidic. And so even the fact that there's twice as many ammoniums in this doesn't matter. 500,000 times more acidic then, or basic rather. So definitely the base will win out in this situation. Okay, so again, it's just evaluating our things here. Alrighty, we've got some tricky ones. So if we look at sulfate, that's a very weak base. Technically, it's not like negligible because this guy is not a strong acid. This one is going to have a pKa of 1.92. And so the pKb of sulfate will be 12.18. Sweetheart, don't pee there. Don't do that. You're being naughty. The new ones always pee all over the house, despite the fact that the door is open to go outside, right? Oh well. So a super weak base. And we have the other one, which is this pesky iron 3 plus ion. If you remember what I told you guys yesterday, those have pKa's of around 5 or so. If you were to actively look this up, Fe3 plus pKa. The pKa of iron 3 plus is in fact 4.58. Remember, this is something you'd want to look up if you have a transition metal or highly charged small metal. Remember, highly charged small metal means it's going to be acidic. And so as a result here, we can see we have our acid will be the kind of victor here. So this salt will be acidic. So just remember, small, highly charged metal ions are acidic. So those they have pKa's, so you would want to look them up. So that would be something again like zinc or aluminum or the iron ions or germanium or stuff like that. So you'd want to look up these pKa's. You'll see that those would be acidic. So stuff like sodium are big and not very charged, so they don't really have, we don't have to worry about them. All right, the last one we have here is just going to be, we have the nitrate ion, which is negligible. It is not really a base because nitric acid is strong, so it's a negligible base. Lithium is a negligible acid. So as a result, this should just be neutral for this particular compound. Just plain old salt. Like sodium chloride is neutral as well because it's made of a negligible base and a large positive, singly positive metal ion. So cool. Alrighty. Any questions on those? Alrighty then, let's take a look at, let's do a couple of your other homework problems here. But we're going to go ahead and look at some of the ones that I haven't assigned for you guys. Yeah, let's do this one. Okay. We're going to do problem 109, which is not one that you're given, but we'll do it anyway. We have butyric acid. It's a got a pKa 4.84. We want to find a couple of things here. Find its pKb. We're going to find the pH of this solution. Hi, little dude. Butyric acid. And then we're going to find the pH of sodium butyrate. Okay, so we're going to just kind of put together a bunch of our concepts here. Oh, we have 2 part B's. Wouldn't that be fun? Okay, so let's go ahead and do this. Hopefully the pKb should be really easy, of butyrate, I guess I should say. Oops. That one we should go, we know right away. So for A, we know that the pKb is 14 minus the pKa, which is going to be 14 minus 4.84, which is going to equal 9.16. Hooray! That one we've done. Alrighty. So the next one, a little bit more complicated. We're going to have to do an ice table here. We're given that we have 0.05 molar. Starting with 0 for these guys. Of course, minus x plus x. So we get x squared over 0.050 minus x equals 10 to the negative 4.84. Remember, that's the opposite of pKa, so when we make it into regular Ka, so that's our Ka, right? So we can go ahead and try our shortcut here. So let's approximate. Let's say we have x squared over 0.05 equals 10 to the negative 4.84. Let's see what we get here. Ten to the negative 4.84 times 0.05 is going to be, oh, I forgot to square root it. Our answer happens to be 8.5 times 10 to the negative 4. Let's go ahead and see if we can do this percentage thingy. And we get 1.7%. So we have our assumption is okay. So x is going to be 8.5 times 10 to the negative 4 molar. And remember, x is going to be equal to our hydrogen ion concentration. And so the pH, therefore, would be the negative log of that. So let's go ahead and do that. Okay, so let's do the log of, log of the answer. We get 3.07. How many sig figs do we need? It looks just like that many sig figs. 2 sig figs. Hooray! So remember, if your assumption puts you at 5%, you got to do the real math. Otherwise, we're okay to just fake it. So we'll have a pH of 3.07 for this particular acid solution. All right. Let's now do part C, which is essentially the same thing, but we're putting in A minus instead. Remember, a sodium salt will always be a strong electrolyte, which will break up fully. So A minus concentration here will be 0.05. So let's go ahead and do part C with that ice table. Actually, I guess since we're doing KB, we're going to want to use the acid dissociation or rather base dissociation. Or if we wanted, we could just use Ka again. Either way would work. We'll get the same answer here, but yeah, actually, yeah, let's do that. Let's just use Ka. It'll be a little bit. I'll just show you something different, perhaps. So this time, we're starting with A minus. So Ka is going to be equal to negative x times 0.05 over x. And that's again going to be equal to 10 to the negative 4.84. Or if you wanted, you could end up with the opposite thing there. If you use KB instead, it would work. You just get you'd use your KB instead, and you'd have basically the inverse of this type of thing. So and you'd have pluses instead of minuses. It'll all work out though. So with this, we can go ahead and try our assumption. We're going to assume that negative. What is this going to be? We can't really cancel out our x's here, so we're going to actually probably have to solve this, aren't we? So if we do this, we'll have to figure this out by doing our math. Technically this was a really bad idea. We should not have done it this way. Because we're going to end up with a negative hydrogen concentration. So technically we're going to have to then bring in our water's original concentration. So this was actually a bad idea. This is going to make it more complicated. So forget it. Let's use KB. It'll be easier in our calculations overall because we're not going to end up with a negative value for our x there. So we won't worry about that. So let's just do the A minus instead here. Oh my gosh. My bad. I like to just lie to you guys as you've figured out by now. I got to keep you on your toes. This will just make things a little bit easier for us to calculate because we'll end up with an easier thing to solve. So 2 plus x plus x. Here's our ice table. We'll get the same thing. Oh my gosh. This will be 10 to the negative 9.16, which is our KB. A little bit easier to use this one because we can just now fake it. So if we do this, x will be equal to, so 10 to the minus 9.16 times 0.05, square root it. We get 5.88 times 10 to the negative 6th power. Definitely that's going to be less than 5%, but we should check it anyway. Divide that by 0.05. That's going to be 0.01%. We're okay for assumption. So that means our OH concentration will be that number there. So the POH will equal 5.8, or negative log of that. Oops. Negative log of 5.88 times 10 to the negative 6, which will equal to negative log 5.88 times 10 to the negative 6 equals 5.23. We still need 2 sig figs, so we're okay here. So pH will equal 14 minus 5.23, which will be equal to 8.77. Hooray! If you were to do it with Ka instead, you would have to get your x value, and you would end up subtracting it from 1 times 10 to the negative 7. And so it would technically work, but it's just more work. It's just easier to do it this way. So, yeah, we'll be good. All right, so your pH there is going to end up being 8.77. That makes sense. We have a base here, so we're expecting it to have a basic solution. All right, and the other one, we did get an acidic solution, which is another way of just making sure that we are in the correct ballpark there. Interestingly enough, let's say we had 0.05 molar of each one. This is an interesting case. If we had mixed these solutions, if we do this, oops. If we assume that these are the same, if we make the assumption exactly, that means that X will be your Ka. And so it's an easy way to do it. And so your pH would just be equal to your pKa. And so we're going to see that if we can make that assumption, then they are going to be the same. So it's a pretty cool thing here. This will be essentially something called a buffer solution. We'll talk about that next chapter, where we have an acid and its conjugate base together. And this will be something where we have the equivalence point in a reaction, where we have equal amounts of our acid and its conjugate base. At that point, the pH will be equal to the pKa. So it's cool stuff. So hooray. So we're done with chapter 16. Hooray, awesome, we've done it. So your homework is up. It's been up for a couple days. It has you looking up some Ka values. You can use the little handout I put in Discord. It's going to have most of those acids. Some of them you'll still have to look up. And so just be aware of that. If there's any that you can't find, throw it in Discord. I'll say, hey, this is what I found. Just use this value. So, or if you have the textbook, it'll have all those in the appendix in the back. So cool. So we're done for today. For the week, in fact. Next week, we'll start on chapter 17, which is yet more equilibrium, just kind of more scenarios of various equilibria. So we'll have a little bit more about acid-base. We'll talk about dissolution of salts and various other equilibria that exist as well. Alrighty, so don't forget, no honors meeting tomorrow. We have the week off. I'll post your questions either later today or tomorrow, so you guys can start working on those for next week. So just remember that. Alrighty, so with that, I'll see everybody next week. Enjoy your weekends. Take care.